Augusta. Thank you, everyone, for having me here. It's really a pleasure to be here. It's a beautiful place and great to have a large audience. So this is the advertised talk, which is about 20 minutes. It's on getting people to remember things. But I thought about getting in front of an HCI audience and thought it would be good to give a little bit of background on the way passwords are implemented in modern systems and how we got there. So how many of you have any background in security? I can see some hands. So, okay. So these are the people you can blame for the way passwords work today. I find it useful when we're going to talk about something like passwords to first say, well, you know, there's security, and when we talk about security, it's to protect against something. And so for security and passwords, it's useful to ask, well, how do you compromise passwords? If you're choosing a bad password, what does that mean, and what are the consequences? Well, there are really two types of attacks we worry about when we're talking about passwords. One is what we call a targeted attack. It's an attack focused on one user. There's someone, and I really want to get that person's password. And so what I do is I take passwords and I keep trying to guess them for that person's account. Now, I could just start with AAAAA, and just go through the set of all possible passwords. That would take a really long time. So what's usually done is if I'm attacking, I'll start with a list that's sorted from the most popular passwords users use to the least popular. So it'll start maybe with password 123456, QWERT, that is going down the top of the home keys, let me in, all of the things that we see when we look at password for each database and see what users are actually choosing for passwords. Now, I may not want one single account. I may just want to get as many Gmail accounts as I can, or as many Hotmail or Outlook.com accounts as I can. In which case, I'm not going to just go after one account until I break it and then move on to the next one, because it might take me a very long time, or I might never compromise an account with a really tough password. Instead, what I'll do is I'll start with the most common password, say password or 123456, try it against all accounts. Start with the next most common password, try that against all accounts. And so these two different attacks, one where I'm focused on one user and one where I'm just trying to collect as many accounts as possible, are the ones you have to worry about. And some of the assumptions that are made assume only one of these attacks, or make the wrong assumptions at the wrong time. So based on this, there are general rules for how we implement password systems responsibly. If you're building a website and you're going to authenticate people by passwords, or if you're building a device and it's going to have passwords, this is generally what you're told to do. First, assume users can't remember random passwords. Then, make users choose passwords that have uppercase, lowercase, and digits. Store passwords hashed. I'll get to what that really means in a minute. And if someone tries to guess the password for an account too many times, lock that account out. So these are generally the rules for implementing passwords responsibly. And let me explain them in a little bit more detail. So users can't remember random passwords. It's something we learned because this was actually tried a bit in the 60s and the 70s. And users, what they found is a lot of users, of course, just wrote the passwords down. And they blamed the users for this for a while, but eventually the system builders got blamed because users kept doing it, and they kept building systems this way. And so they decided to abandon this idea, because if you just tell someone you have to remember this 12-character string, we're not really built for that. And so there's also this mythology of the incompetent user. And my favorite example of this mythology, as it comes with passwords or people remembering secrets, is this quote from a book, Network Security, by Charlie Kaufman, who I used to work with, Radio Perlman, who's quite a famous researcher. And it says, humans are incapable of storing high-quality cryptographic keys. They're also large, expensive to maintain, difficult to manage, and improve the environment. It's astonishing these devices continue to be manufactured and deployed, but they're sufficiently pervasive, and we must design our protocols around implementation. So this is the engineer's view of users and the mythology of the incompetent user. So we can't ask them to remember something random. So they have to choose a password. Why follow these rules? Well, remember what our model of the attack is, that the attacker is going to go from the most popular password to the least popular password. You want to make sure they don't have one of the most popular passwords. You don't want this cluster of popular passwords that looks like this, where 2%, close to 2% of users are choosing password, a bunch are using the null string, and and so on and so forth. This is based on real data, but it's not exactly real data because there's certain data I can't use. So if we have this model where they're going from the least popular, from the most popular to the least popular, we're hoping that these rules eliminate those popular passwords, that we now have passwords that are harder to guess. Storing passwords hashed. How many of you know what that means? Okay, so basically, right, there's a number of ways we could keep records about our users so that we can verify who they are. We could just keep their name and their password, but then if someone breaks into the system, they've got the list of everyone's name and everyone's password. So instead, we tend not to recommend this. And we say, no, you're really, that's an incompetent thing to do. What you want to do is you want to keep the name. You want to give each person a random string. And then you want to not store the password, but a hash of that random string and the user's password. And when the user comes back to log in again, you take whatever they say was their password. That random string is information. It's stored right there in your file. It's called the salt. And you see whether it matches. And now, if the attacker breaks in, instead of just reading the passwords, they have to go and they have to check all these possibilities to see if they're the ones that would have the right hash. And the reason we gave each user their own unique string is that way an attacker has to do this work again for every user. So now the attacker has to go in and spend the computation to calculate this hash function for every possible guess of what the password might be. And if they've got lots of computation, they might be able to break 30 or 50% of the passwords, but if you've got a really strong one, they may not be able to. Finally, lockout, this is pretty intuitive. Lockout accounts if there are too many incorrect guesses. Well, right, if the attacker is just going to make a lot of guesses, a great way to stop them is just deny them more than a certain number of guesses. Okay, the problem with these, and these rules that we've followed and that are sort of the received wisdom, is that they're pretty much all wrong. They're all used today, and they're pretty much all wrong. First of all, the second part of this talk is I'll get to the assumption that users can't remember random assigned passwords. In fact, we're quite capable of remembering random things in the right circumstances, and if it's not abused by being used too much. So probably not something you want to do for a website, but for a device you use every day and you really care and that keeps your passwords for everything else, is actually not true. The advice that we should all be using special characters, uppercase, digits, all of that is ineffective and actually sometimes harmful. Storing passwords hashed, if you actually care about security, it's insufficient. If you don't care about security, it's unnecessary. And locking out accounts actually is quite dangerous. So I'm going to explain why all these things are true in the reverse order I presented them. So I'm going to go back up and starting from the bottom. And then we'll finish up with whether users can actually remember random passwords. So locking out accounts if there are too many guesses. Now, I presented the two types of attacks. There's the one if you want to get one user, and there's the one that if you want to get as many accounts as you can. So locking out accounts was sort of designed for someone who's attacking one user. So if you're going to guess, right, lots of passwords for this one user, we'll lock out that account, which sounds sensible. But think about what happens if the attackers are doing the other thing. They want to get as many accounts as possible. So they do what I described before, where they pick the most popular password, guess it against all users, then they pick the next most popular password, guess it against all users. What are going to be the consequences of this? Anyone want to volunteer of what goes wrong here? Yeah?
A lot of people are locked out of their accounts.
Everyone's locked out of their accounts. Yeah, you've just locked out. If I'm running Outlook.com and we have 500 million users, we now have 500 million users locked out of our accounts. If I'm running the UBC servers, we now have everyone locked out of their accounts, including the administrators who are supposed to be able to unlock everyone from their accounts. This is really bad. You can't do this. So the consequences of this are, it's something you can't just say, okay, everyone better go do this. You have to have something to make sure that this really bad thing doesn't happen if you're seeing the attack you didn't expect. Okay, let's go to the next piece of received wisdom, that we all should store hashes, and you'll see whenever you have, there are websites that don't do this and they're broken into and the password files are leaked, they get negligence lawsuits because everyone's supposed to hash passwords. Well, in fact, hashing is not really that effective because about half of users will have passwords predictable enough that the attacker can go and just do the random thing and guess. And so what we want to do is make sure that the attacker needs to do more than that. And so if you actually care about making sure that when you store your passwords on the disk, if the attacker gets that storage file, they can't do anything, you want hardware. You want a hardware security module that performs your hash function with a key, and a key that's only stored in this hardware security module. So you can imagine a little piece of hardware you can throw into your box, and it would have a set key function, so you could store the key in there, and you can presumably do that in some secure cage somewhere where you keep the secret key, not online in case hackers break into your systems. Then you take this piece of hardware, you put it into your systems that are online, and they have this set key function, and they have this hash with key function that lets them hash. And without this key, you can't do the hash. And of course, you can imagine a get key function that would get the key out of the hardware. But we'd never implement that, right? You'd actually design your hardware so it's like a roach motel. Keys can go in, but they can't go out. They can only go in, and they can be used to hash. And if you have one of these pieces of hardware, it doesn't matter if the attackers compromise your system. If they can take the files away, if they don't have this key, the moment they lose access to your hardware, they can no longer they can no longer try to guess what those passwords were. So you'll have some other things in this hardware. You'll want to rate limit how quickly people can guess. And as I said, you probably want to make sure this is all initialized somewhere safe where you store this key that's not on the internet. And this would, in just about every password compromise incident you've seen, this would have completely eliminated the damage once the attackers were kicked off the system, better than just hashing alone. Yet, the rhetoric that goes on with how we store passwords is, if you don't store your passwords hashed, you're grossly negligent. So if you're not protecting the 50% of people who happen to have really strong passwords and might still be safe by hashing these passwords when they're in storage, then you're grossly negligent. But no one's actually protecting the other 50% of users. And we could stop asking users to have such strong passwords and follow all these rules to make sure that it took millions and millions of guesses if we just use this hardware, but nobody's actually doing it. Okay, so lastly, choosing these special characters, uppercase, lowercase, digit symbols. We've been told that this is something we really need to do. Now we actually have, thanks to some break-ins in the last decade, we have a lot of data on how people actually choose passwords. So this website, RockU, had 32 million users. The passwords were in plain text, so they were not even hashed. Someone broke in, got this set of usernames and passwords, and published them for all the world to see. So we have a lot of data here, and we know that almost 0.9% of people chose 1, 2, 3, 4, 5, 6. They didn't even have a length requirement, a minimum length of 8. Ask their password. So there's guidance on how you're supposed to make users choose passwords that requires those uppercase, lowercase digits, and symbols. And we could look at the RockU data and say, okay, of the people who had passwords that complied with that guidance, that had done all of those things, what was the most popular password there? And it was password with an @ symbol and a 0, which was, for all effectiveness, just as popular among that set of passwords as 1, 2, 3, 4, 5, 6 is. So all of this work and all of this pain to try to enter uppercase, lowercase digits, and symbols had effectively no benefit. And intuitively, there's some reason for this. You think about what would users choose if we gave them no rules. Well, the Wild West, what RockU did, you can choose anything. You get some kind of distribution of really popular passwords like this. And now you think about, well, what happens if we put in rules? Those should always make things better, but rules have side effects. So let's start with, we're going to require 8 characters. Well, our most popular password is password. It is 8 characters. Once we require 8 characters, that's going to occur more often. So now, okay, we're going to start requiring numbers. Okay, so password went down, and some people added 1 to the end, which is typically what you're going to do. But now we have some savings there of numbers. Now we have link 182. Where did that come from? Well, a lot of people choose bands. If you have to choose a digit and you want to choose a band, there it is. There's not much to choose from, but link 182. So we made that one more popular. I actually think the Korean band 2NE1 was probably created just so that people would have better passwords. And of course, then we require symbols, and people start getting more and more confident. Now they're really confident that they're doing better stuff to protect themselves. So, hey, I can make a good password now that I now have all these rules. So now people, as you saw, roughly the popularity of the most popular password was the same, but people were putting in more work. They felt more confident that they had done something useful there. So all of these rules that we're told we're supposed to use actually don't help either and just hurt our usability. This is our alternative password policy that we've proposed, and we've in a more technical talk, there's infrastructure for how you do this securely. The rule is choose any password you like, as long as it's not too popular. So we could do this for, say, a site like Outlook.com, for Gmail, where you've got hundreds of millions of passwords. If your password is more popular than, say, 1 in a million, you can't use it. If it's less popular, we don't care. Because 1 in a million would be a huge improvement over just about any of the other systems that are used today. So to illustrate that, right, take where we get with all of these rules. This is what you get with a no password more popular than 1 in a million strategy. Our line is invisible because it's 1/10,000th of a percent is the popularity of the most popular password. And you can implement this without actually storing people's passwords in a way that someone would be able to get this popularity list out. And if they got the even if they could get the popularity list out, all they'd find is here are some passwords that will work if I'm willing to make 1 million guesses, which will, of course, we're going to start noticing that there's some IP addresses that are making hundreds of thousands of guesses unless you have a heck of a lot of IP addresses. Okay, so this is where I take the break and move on to the part of the talk where we talk about random passwords. And so there are some cases where the work to memorize a random password is worth it. I think the best one to illustrate is, of course, a lot of people now use password managers. And the password managers ask you for a master password. So that master password protects all your other passwords. It better be strong because that's where all your passwords are. There's some other tools that do encryption that basically you're encrypting your whole file system. And so it's another situation where basically everything of value to you is protected by this one key. And if you work for an enterprise like Microsoft, basically whatever is your login password, that gets you into everything in your company. And so effectively, all three of these are the same thing, right? These are putting your eggs in one basket. This is the one credential that protects all of your other credentials. And when you're putting all your eggs in one basket, you want to protect that basket. It's worth spending 10 minutes to memorize something if that's the only time in the rest of your life you're going to have to remember a password. So what about this assumption that users can't remember random assigned passwords? And so this is the advertised part of the talk. So let's step back a bit and think about the assumptions about when we generate passwords and how we construct accounts and how computer scientists think about this. So, right, computer scientists, when they want people to remember things, or they want you to remember a password, right, we have our familiar metaphors for how we think about storage, right? You want to store something in the user's brain, well, you read it, and there's this write operation and this read operation. And so when they create this account, you need to write something to their memory, and when they log in, you're going to need to read from it. So you've got your read-write head, and just like if it was a hard disk. And right, we explain the problem using this metaphor. So you've got your write, you've got your read, and you see these reads fail. And when the reads fail, when people aren't remembering their passwords, we say, okay, they can't remember a random password. We need to make them work harder. So we need more power, we need more time. And so the metaphor, should be something more like etching into stone, where it's really hard, and it's gonna take a few minutes. It's really hard. But if you just worked hard enough, surely you could do this. And when we try to write, we try to read, and the metaphor still fails, we say, oh, we still need more power. We just need more power, or we just need more time, or it doesn't work. So instead, we need to realize, okay, time, power, and range doesn't equal memorization, and we need a better metaphor. Because your brain's actually designed to forget things that are random that you only see once. Otherwise, we'd all be just totally consumed by random information and never be able to focus on the stuff that actually matters. And so instead of this model, it's actually not quite the case, but think about not single session memorization, but maybe if you could memorize over multiple sessions. So a better metaphor for human memory might be as this beach where you can see this large amount of randomness etched by water, which certainly doesn't have the power of an axe pounding into the ground, but over enough time and repetitions is certainly able to etch into the stone in a quite effective and amazing way. So, right, talking about spaced repetition, if you have enough repetitions, you can memorize something. This is something that should be intuitive to all of us because you all got into grad school. And how did you get into grad school? Most of you probably used some spaced repetition to study in order to get into undergrad for the SAT, in order to get into grad school for the GRE. And right, you did this process where you exposed yourself to information over and over again, reading it until the point you found out you were recalling it ahead of time. And this works. So in this model, right, you have this lots of writes and reads, and eventually you can take a break and go into your exam or go to log into something, and the reads actually work. So how do we make this work for passwords? And so this is some images of the system we designed. So we let people, to differentiate here, we let people choose their own password, and then we gave them a secret to memorize. So when people signed up for our system, they would choose a password, and then whenever they log in, we say, okay, type your password, and now type the security code. And they would just copy it from right above. And sometimes the security code was made up of words, and sometimes it was made up of letters. And they would type in this case, 4 letters or 2 words. But we changed things each time they'd log in. So the second time they'd log in, the code wouldn't be right above there. Rather, it would appear after a very small delay of a third of a second. And the next time they logged in, that went up to 2/3 of a second. And then and eventually, right, here it's going to take 10 times that. They just type in their code before it even appears, because at this point they memorized it. And we never told them to memorize it. They just have memorized it subconsciously. They've done this enough times that they're like, okay, I don't even have to wait for it anymore. So that's what we did. And once we observed them enter it a few times without 3 times, without us having shown it to them, then we give them a second part of the code. And after that, we gave them a third part of the code until they were learning either 12 characters in total, or they were learning 6 words. Either way, the space of each encoded 676 possible values. And so if you take that each word was 676 possible values, and 2 letters is 676 possible values. So when you take 6 of those, either 6 words or 6 pairs of letters, you get about 56 bits of data, 2 to the 56 possibilities. So how do we test this? So what we did was we created an Amazon Mechanical Turk distractor task. And first we just had people do that distractor task to get them interested in our study. And this was, how many of you are familiar with the Stroop effect, where you ask people to read colors, and then the name of the color is the word, and then but it's actually written in a different color. We made something that looked like the Stroop effect. So here your job was to type a key on the left hand of the keyboard if the word was left, a key on the right hand side of the keyboard if the word was right. But sometimes the word left would be on the right side of the screen, and sometimes the word right would be on the left side of the screen. It was completely random. And we called this an attention test. It looked like a probable psych study. And so we had them do this, and after they'd done this once, we paid them for it, and then we said, hey, would you like to be part of this larger study? You can just do that attention test again 90 times. And you'll have to wait 30 minutes before you do it each time. So in a 15-day period, you're going to need to do this 90 times. Each time you do it, you'll log in. We're going to give you a short survey to find out if you've had any caffeine or how long it's been since you've slept, so we understand something about your state taking an attention test. And then you'll take the attention test. And so they'd sign up. Most of the people thought this was, most of the people who had done this on Mechanical Turk thought this was a pretty big deal. We were paying $19. And so they'd sign up. They'd, again, do this brief survey, take the attention test, and then they'd have a 30-minute wait until they could do it again. Of course, to do it again, you have to log in again. And each time we'd be taking them through that process where they'd be learning their security code. So, they'd type in their password, and the first time they do it, we'd say, hey, we have had some concerns about the security of the passwords. We're adding the security code. And so that's how the process worked. And one of our questions was, well, would people drop out because there was this extra work of the security code? So we had three groups. We had a control group. We had the group that was getting a set of 12 letters in 3 chunks, 3 sets of 4 letters, and the group that was getting 3 sets of 2 words. So a total of 6 words. We gave only a reduced probability of the control group. So 40% were given letters, 40% words, 20% control, all assigned randomly. And the control was basically to figure out the difference in dropout rates. And indeed, there was a difference in dropout rate. 85% completed for control versus 75 for the other two, or 76. And so we wondered, well, is that statistically significant? Not quite, but there's probably an effect. People are most likely dropping out because of the extra work, for about 10% of people. Because if you look where they would drop out for the extra work, it would be in the first 2 or 3 games. After they've learned they have to enter the security code. The first time they play the game, they've just signed up, they haven't. The second time and third time, they've now played the game and they have to enter the security code every time. And we didn't see any dropouts for the control group, but we were seeing dropouts for the other groups. Okay, but once we were done, almost everyone who was in those letters and words groups had been remembering their security code. They'd received the whole one and gone through it, and they'd gotten to the point where they'd proven they'd remembered the first one by entering it ahead of time, and they'd proven they'd learned the second one. And so they were there, but there were 6 people who didn't. So you might see this as about a 5% failure rate for their ability to learn. But that would actually be the mythology of the incompetent user who's not learning. In fact, these people were learning pretty well. There's this interesting fact that the 4 of the 6 who failed to learn didn't fail to learn the first code. They didn't fail to learn the third code. They failed to learn the second code. So we assigned them the first code, they learned it. We assigned them the second code, they didn't learn that one. And there's an interesting challenge with the way we designed this study that we probably, in future versions, we've done it a little bit differently. When we assigned them the first code, we didn't tell them there would be 2 more codes if they learned the first one. When we gave them the third code, we could say, hey, congratulations, you've learned the first 4 words, the first 8 letters of your code. Here's the last part, you're done. You're not going to get any more. For the second one, we couldn't say that. We had just given them more work to do, and we could say, this is the end. You're done here. Don't worry about us giving you more work. So we followed up with those participants who had mysteriously stopped learning on the second code, and we got answers from them. And the answers indicate quite clearly that they were in fact learning. They were not just learning the code, they were learning what the study was about. And my favorite quote is the one at the bottom where the participant is quite indignant and is worried that says that even his dog would not be tricked into memorizing more stuff. So this is it's tempting to assume that people are just not learning here, but in fact they're learning quite well. And these are some curves that indicate the learning. In the x-axis, you'll see the login attempt, the number of times they've tried to log in already, and whether they successfully entered the code before it appeared. No one's going to do it on the first try because it appears instantly, and you don't really even have enough time to start typing the first few times. So you start seeing success around 5 or 6, and on average success after about 10 times. So they've got about a 4 or 5 second delay there, 3 or 4 second delay there, and they're able to learn. Now, of course, they can't start learning the second one until they've shown it. We've shown it to them, which is why the green line that represents them learning the second set of codes starts so much further after the first. And you might wonder, well, does it get harder to learn the more information you have in your head? So if we compress these lines, where we start each person when they first got their code, we can figure out how quickly they were learning these codes relative to each other. And in fact, that we see that they learned the first code the slowest because they didn't quite understand at that point that they could just learn the code and type it in before it even appeared. And then they learned the other codes just as quickly, or in fact, more quickly. So the last question, of course, is does this stay in memory? And so 3 days after they completed the study, we followed up with them. And we said, hey, would you like to earn another $1? You can come back and enter your code, and we're not going to give them any hints. We're just going to ask them to type it in, and even if they wait 10 seconds, we don't show anything to them. And so we find out that just about everyone participated in the follow-up. The numbers look like it's only about 88%. Some of them followed up too late. Some of them accidentally found out about the follow-up too early. And so we had a great response rate, but it's actually a little artificially low here. Of those, 82% in the letters group and 93% in the words group were still able to remember after that 3-day interval. And that's an average of 88%. It's not quite statistically significant. So words look promising, but we can't say for certain that they're better. Now that means about 12% of people forgot, which is not ideal, but it's worthwhile to have a basis of comparison. You might be thinking, well, some of them wrote it down, and so your numbers are artificially inflated because some of the people probably were writing it down. We asked people were they writing it down, and the people who were writing it down didn't actually do any better than the people who didn't write it down. They probably threw out the paper. Some of them probably threw out the paper after the study was done, but before the 3 days elapsed, since we didn't tell them we were following up. And when you compare to previous studies of user-chosen passwords, where people usually are told, choose anything you want, you're going to enter it twice, and they're not told that they're going to be followed up within 3 days. And it's roughly the same methodology. The recall rates for those max out at 74%, which means when users are choosing their own passwords which don't have repetitions, they're forgetting 26% of the time. If they've had a couple of weeks of repetition, they're forgetting 12% of the time. So this isn't even necessarily worse than user-chosen passwords. We have this myth that people can actually remember things if they get to choose it. The reason they mostly remember things when they get to choose it is that they get to choose something they're already using, which is ill-advised for any of these situations where you actually care about security. So the one downside, of course, is that this will degrade over time, as any memorization will. The general findings for spaced repetition is that it lasts roughly as long as the repetition, as you've been trying to memorize something for. So if you tried memorizing something for 2 weeks, it starts to fade after 2 weeks of not using it. So after 2 weeks, the recall rates went down to about 50 to 60%, and you'd expect them to continue going down. Of course, if this is a key you're continuing to use, that's not going to be so much of a problem. If you've been using it for 6 months before you go on a 2-week vacation, you're probably okay. So to close, in summary, I think what one of our participants wrote summarizes it best. It was surprising that you did this follow-up, because I did not expect it. After having entered the code so many times, the words are branded into my brain. And that was what was really fun about the study. We didn't really tell people that we were trying to train them to memorize something. They weren't trying to memorize something. And what we find in these studies is people are often really surprised by their ability to memorize things because they think they have bad memories. If you ask them, they'll tell you they have bad memories. But when you give them the right tools, they actually find they're quite capable of memorizing things. So what I hope you'll take away from this talk is this: most of these things that the security people will tell you about passwords are just not right. Most importantly, that for the really important situations, it is possible to memorize random passwords. Thanks very much.
We have 10 minutes for questions, and everybody is welcome to stay after 1 p.m. here to socialize and continue discussions. First question is always from Kelly.
So your last point about blocking out accounts and opening up to attacks, do you have experience with whether hackers maliciously guess incorrectly in order to lock out either targeted or general users, and then send them, for example, an email saying you've been locked out, here's your recovery mechanism, so that they are actually getting, and say, have to give us your old password to set your new password.
It's a great strategy. I can't comment on whether it's used or not.
You don't know or you can't comment?
I'll leave it there.
I am wondering, so my password has something like 22 digits, and how I learned it is taken from 3 sentences that I can easily memorize. So that's something like, my wife's name is blah blah blah, we met in Edge, and then you just take the first digit and the first letter of each word, and then you memorize it in maybe 20 minutes. And then I'm confused if you're creating a sophisticated solution for a very easy problem.
So, lots of people will say, I have an easy solution for this, which is, I do this. It's great if you do that. The moment you make that the common way to choose a password, the moment you give prescriptive advice on how to choose a password, you are going to cause a lot of people to do the same thing. This is actually the problem with the moment we started telling people to use digits and special characters. When you tell them to use a digit, that's a stimulus. Lots of people have a common response. Add a 1 to the end. When you tell them to use an @ sign, suddenly you get a lot of things with A's turned to @ signs. Or now people are more likely to use words like cat, bat, hat, because they're told they need to use something with an @ sign, and they go, what can I use which has @ in it, so I can make something clever that that has, or the hat symbol. So the shift 6, also known as the caret. Or can I create a sentence with carrots in it? So anytime you say, oh, there's this common thing, there's this thing you can do that works for me. I think the one that used to be prescribed was take your favorite song lyrics and take the first word of them and make a password out of that. Well, there's only so many, right? Once you start doing that and that becomes popular, there's a zip distribution of how popular songs are, so anytime you get one of these things, it causes people to do a common thing. So we strongly recommend against just about any prescriptive guidance for passwords, because whenever any prescription is a stimulus that may cause a common response. Even if it's do something unique, you'll get something unique. The string is something unique as a response from some fraction of people. So generally we recommend systems that are designed that they let users choose whatever they want, and then they look for things that are popular, and then they just get rid of, they say, oh, well actually, this is a bad idea, and here's why, and do something else. But 90% of people are going to choose something that's relatively unique, and so you don't have to bother them at all, or tell them to do a lot of extra work. So for web passwords, that certainly works. And yeah, we can try things like that when you want to have a provably long string. But if they take basically my birthday, my wife's birthday, right? It's something attackers will have. You can't guarantee whenever you're asking the user to generate the string, you can't guarantee that you're going to end up with something that's secure, because you don't know what the user's doing and what's going on in their head. And the attacker may have a much better understanding of them than you do. So they may know their daughter's birthday. The attacker may know their wife's birth date or where they met. And so we can't know whether a string is secure or not unless we generate it randomly.
Very interesting, thank you. So, I think what you've shown is that people can memorize things if they're if they try, or most people can. I guess what I'm interested to know is how do you actually see this playing out in a system? I mean, do you see it like, oh, you get your new Windows box or Mac box, and it gives you start out and it says, we're going to give you a password, we're going to help you, we're going to train you to do it, right? And then for the next 2 or 3 weeks or 4 weeks or whatever amount of time is needed, it helps them try to learn it. But then, of course, people might be around and they're going to learn it too. Like, I'm just trying to figure out how this would actually play out in a real system where they're trying to learn a password. Because, of course, that password is going to get displayed X number of times over, several, weeks or more.
Sure. Well, so one type of deployment is an enterprise deployment. So when you're in an enterprise, right, you're mostly sitting at your desk. So we can make sure that people are only entering their passwords when they're at their desk, and if they want to have remote access during their first 2 weeks of deployment, we can make them do something more arduous. So in that type of situation, we have much more control over the environment. I think one of the key applications here is a password manager. And when you use the password manager, right, the first, you set up a password, and then over 2 weeks, it weans you off the password and moves you onto a security code. And then it's just a matter of, well, we're not going to show you, you need to click something saying you're alone before we show you what it is. So when it's your job to get your screen out of whoever's face it is when you're entering this. And, when you look at what the threat is, well, someone can see your screen. If they can see your screen, they can also see you typing on the keyboard. So any password you were entering was probably not safe. There's not that many situations where people can see your screen and see those letters up on the screen, but they can't see what letters you were typing into a keyboard or what you were going to type into the screen. So we're not so worried about that because, again, the user has some control over that, and we can restrict what happens during that period for something like an enterprise use. For an enterprise use, it's we as the people who design the system who care. For a password manager, it's, well, the user's doing this because they actually care about having this one master password in this, right? And so there we have a pretty good sense that the user cares, and if the user doesn't care, well, that's right. It's their system.
So, I mean, I think you've largely addressed it, and it is very tricky, though. I mean, I spent a lot of time in an enterprise situation sitting at my desk, and I got students around me.
Sure.
Right?
Yeah.
And, and I actually, to the point of, well, when you can see people typing, I mean, I see people typing their passwords all the time. I have no clue what their passwords are. I mean, because they're typing way too fast. But if I saw it in front of me, written out, I'd be able to read it, no problem. But there'd have to be a lot of nuance around when they can get by with their original password and when they have to use the code, because there's times I have to get at things and I've got students or colleagues or whoever around me, right, and I don't want to be in training mode at those particular times.
Sure.
So I think it's a bit trickier than
you would probably want to have an override for that situation for during the training period. For sure.
So during your mechanical tour study, you said you noticed a pattern where people were forgetting the second word more often.
Yeah.
I'm just wondering, have you looked into, or could this maybe be explained by the serial position effect? It's, I think it's from psychology. It's where if you're role learning a sequence, then the number of errors that people make tend to be distributed around the center. So that could be an explanation as to why people make more mistakes in the middle.
So there were a total of 6 people who made mistakes, and 4 of them were in the middle, and we had the explanations for all 4.
Oh,
and
okay.
Those 4 seem pretty convincing. That I mean, we didn't ask them leading questions. We asked them, hey, we're trying to understand what went on here. What was, can you help us understand what your barrier to learning here was? And they came out and told us, right? They've been paid. We actually paid them, more for giving us a good answer. And so I'm pretty confident that we know the answer on that one.
So what are the answers?
Well, it was those 4 people who said, of course I didn't type in the password before, the code before it appeared. Then you'd give me another one. I don't want to have to learn anymore.
Isn't there ways you could integrate some other memory learning strategies, like the ancient practice of topography or images to associate with knowledge?
Yeah.
bits of information, so you could just have like an image or a map or something that people could associate their learning with, and then that gets displayed every time in repeated fashion so that you.
Yeah, we've run another study. It's not published yet, and it was rejected from Kai not because of accuracy, but purely on, well, we don't think this is a great research direction, and so sorry. And that's kind of Kai. But yeah, I had an intern who was really excited about using a number of different strategies. He actually developed these memory castles that you could walk through, and he built this technology, and it was really a little heavyweight for this. So we ended up doing a study with different heuristics. One was that we had people create peg words that they could associate with our random words, and one in which they would create sentences with our random words, and we'd make them create the sentences, and then we'd keep the sentences up for a while, and they were somewhat effective. So yeah, but they were also a lot more work. And one of the beauties of the approach I showed today was that people weren't trying to learn at all. We never told them to learn. We never asked them to learn. We just told them you can enter this code whenever you like. And they didn't actually feel like they were doing, they felt like they were doing a menial task of typing this stuff in. But when you ask someone to type something in, it's very tractable, right? It's not that much to ask of them. When you say memorize something, right, that creates anxiety. Will I be able to remember it? It's real work. And we never did that to people. Whereas once you start using those heuristics, the good news is you're bringing them in on the game, right? You're making it more fun, but you're also telling them, hey, this is your responsibility, rather than just letting them learn accidentally. Yeah, do you still have a question? Yeah. Oh, no. Yeah.
I was just curious about, so in your prescription, but how would you, in practice, verify that popular passwords? I mean, no one is really choosing a password saying, I want the most popular password when I'm creating this. So when you're saying I'm creating when I'm gonna put my new password in, how would you know in your system
Well, for a system like Hotmail, we have 500 million users, or Outlook.com. We have 500 million users. Each of them has a password. If we can keep some data around that lets us know whether it's what those passwords are enough to know what's popular, we can do it. So the trick is in how to keep that information around without endangering users. And you can do it, or if you're familiar with Bloom filters, one of the naive ways to do it would be to just use a plain old Bloom filter. There's these more complicated structures called count-in sketches, really minimally more complicated. And you can, instead of having with the Bloom filter, you have a bit 0 or 1. It can count. You can actually track popularity with these things. And one of the beautiful things about them is they have a false positive rate. So 1 in 1,000 users, you're going to tell their password was popular when it wasn't. And this is going to annoy 1 out of 1,000 users who will now have to do the task a second time. It's slightly harmful, but just 1 out of 1,000 users will have to do a little extra work. If you're the attacker and you try to enumerate all possible passwords, you're going to be told that 1 out of every 1,000 is popular. So when you go look at all the 8-character passwords out there, the number of falsely popular passwords is going to outnumber the truly popular passwords by orders and orders of magnitudes. So you can create one of these structures, keep them in memory, and really have very little security risk. If I can point you to a paper on how to do that, if you'd like. It's the one, I had a number of collaborators at the beginning. It's the one that has Michael Mitzenmacher on it. Because he's into that kind of data structure. Did you get a question yet?
Yeah.
Yeah, go back there. Okay.
Yeah, so I was wondering, since memory is so context dependent, if you've done any studies where you change the context of the users to see if they can still remember the code, so like you change the science tree, for example, to see if they can still remember the code.
We didn't intentionally do that. I was just lazy, and in this study, because I wasn't using the widget I had built that would display things, it was just 3 input boxes. So in fact, we did change the context a bit. I would have probably gotten better results if I hadn't. So yeah, they didn't even have to enter their password ahead of time. We just looked at their worker ID. And so we would have probably gotten better results if we had made them, enter their password first. The reason we didn't is we still wanted their data, even if they'd remembered their chosen password. We still wanted their data on how well they could remember the code that we assigned to them. Okay.
Yeah, and in your second or in your study, you didn't talk about the demographics of the participants. So I was wondering, like, if there was an effect on the level of successful memorization of the passwords in terms of different people or different ages, different,
We would have. The only way we would have been able to find any effect is if we looked at that 2 weeks later data, because the memorization rates were so high. Right, when you've got forgetting rates of 10 people out of 100. Then you try to break that down for demographics. It's the data is way too small. You won't be able to find any effects there because you don't have that many people forgetting. And that's one of the challenges in just looking at the errors that were made to figure out why they were going on. Some of the people who we report as forgotten had just transposed a couple of letters. You can try to do that kind of statistics, but it's right. You then need thousands of participants if you want data on a problem that occurs 5 or 10% of the time.
But what about with the representativeness of the sample itself? You said it's about 100?
So we had about 100 in each group, and it's a standard MTurk sample. So it is it's more diverse than students, but there are more people who are unemployed than typical. They're lower income than typical. It's not a perfect sample of the population. There were a number of people in their 50s and 60s, and so it was definitely more age diverse than the student sample.
Just related to the last question, I was wondering about the motivation. So as I understood, it's $19 plus 1, and then I think the ordinary user might think, okay, I don't have any interesting stuff in my email I do have to protect, I don't bother about that. So if you want to put it in the real practice, so who would bother sitting there for a long time for the password to learn it?
So part of the beauty of this is they're never sitting there for a long time. So this took, I guess I didn't cover the amount of time consumed, but this took about 10 minutes of time divided by 90 logins. So at any given login, you were only slowing them from getting down to their work by about 10 seconds. So, you're not asking them to memorize something for, spend 10 minutes thinking really hard about X. It's, each time you log in, there's going to be this tiny tax of, type in what you already know and type in, 12 characters. And so, it's not as painful as you make it sound. That said, if the user's not motivated, if they really don't want to do something, they can still write this down. They can still do other things, which is right. If they want it for their password file, right? If they're using a password manager and they want their password manager to be secure, they'll be invested. If they're working for an enterprise, it's the enterprise's job to explain to them why this matters. If they don't want to do it, you can't force security on people. They can always learn the 12 characters and then paste it to their Facebook page. Nothing you can do to stop that. Same thing they can do with it. They can take their fingerprint, take a photocopy of it, and scan it in and paste it to their Facebook page if they want. There's only so much you can do. Yeah.
I just want to follow up on Joanna's point, in that it seems like one of the issues is that it may take too long to learn these things. Like your study, it took quite a while for you, just 12 characters or whatever. Yeah. And I'm just curious, why did you decide on 2 words at a time as opposed to, like, if I just saw 6 words at a time, it doesn't seem like it's so much harder to memorize 6 words at once. You could go through this process much faster.
You could.
But I'm more curious why you decided to do it the way you did as opposed to just maybe showing more.
Among other things, we were, so in future versions, half at a time, we didn't want it to, if we had given them 6 words, I think that would have seemed really intimidating. The nice part was they started off with 2, and then once they learned the 2, they got 2 more, and they'd already learned 2, so it doesn't seem like that much more. Sort of the boiling the frog story is, of course, apocryphal. Frogs will jump out of the pan. But we were sort of trying to boil the frog, and what we found out was we should have probably done 3 and 3. That 6 characters is reasonable. 12 is probably a little much. Breaking it down, we were trying to make it as low stress on these people as possible. So not give them anything that seemed intimidating.
Don't you think that you might be kind of like that first point you had when you say like the original fallacy was like users aren't capable of memorizing these things, so we're gonna show you why that's wrong. But now you're saying we don't want to like give them too much because we're scared they're not gonna be able to handle it. It seems like it's almost.
Well, again, we were trying to test with totally unmotivated users, right? They had we couldn't create anything that they could lose because they would put it in danger. So we were working with the least possible, right? The least possible motivation level of users, which is good, right? You want to test in that situation and prove that it can work. So yeah, we could have asked more of them, but it's sort of part of a design philosophy of how much work you ask out of people and how you want to turn things out. It might have worked fine. It's be a great thing to see experimentally tried. Yeah.
So you mentioned your picture shows a brain. Of course, the brain has lots of pieces to it.
Yeah.
My experience, I think most people's experience, is you get down to the muscle memory eventually.
Yeah.
So you've already, I guess, answered a question about implicit memory, sort of what's in the background. But to the extent that it's tied to your physical keyboard, do you see an issue if you end up, would you be better off to have a separate password on your iPhone versus your computer so that you don't get cross-modal interference, trying to use the keyboard on your iPhone, which is grossly different than the keyboard?
This is one of the reasons why I really don't like passwords with letters and numbers, because among other things, I will make phrases with the word to in them. And when Microsoft introduced, we had touchscreen phones where you would enter your password so these were actually, traditional phones that sit on a desk and are connected with a wire. And they're internet phones, at least. These we're not Luddites, but this was 7 years ago. They were deploying these things, and IP, right? It was part of a whole get everyone to get rid of their phone systems, move to IP, and they asked us to enter our same passwords on those phones. And I called up our tech support because my password didn't work. It was because I was typing TO when I should have been typing a digit 2, or right, that muscle memory does kick in. So if you keep it all lowercase letters, at least you're at least the same positions generally apply. So that's one of the reasons why we didn't do any digits, we didn't do any symbols. But yeah, it's definitely a problem. And some of the other systems we've built have been on the premise that people should get to choose passwords that are just lowercase letters because it will work better when you change modes.
So there's time. I had a second question. Anybody else?
Fine, go ahead.
So you talked about enterprise, and one of the problems with enterprise solutions is they're usually run by Nazis, and these have all these rules out. So, for example, my daughters, when they're younger, had accounts at UBC,
right.
And for whatever reason, they didn't remember their passwords. And we tried to retrieve them, and we found out the only way you could retrieve them was if they came down between 9 and 4:30 to an office that I didn't even know where it was. And of course, they were only using these passwords to get onto the Wi-Fi on the weekends when they came to work with me because, I was taking care of them. So it was crazy. In an enterprise situation like Microsoft at work, where many people are working side by side in a group, has there been consideration for things like, if I lost my password and I need to recover it, why can't I go to the person who's one cubicle over, who knows me, and the system knows that they know me? Yes, they act as a sysadmin because they know more than any sysadmin that it's me, and not as a sysadmin. But they verify that it's me.
At Microsoft, since I joined 7 years ago, 7.5 years ago, there's been a process where what you do is if you've lost your password, you call up IT, they say, okay, who's your manager? Can we email it to your manager? Your manager's not available. Name someone in your group we can send it to. And they will do that, and then, right, because they must trust that person, and if that person messes up, they can fire that person.
It seems we leave the humans out of the loop sometimes on these solutions.
Right, and we also tested a solution. So before Facebook now uses this, but we tested a solution where you could go to your friends And if you lose your password, they'll send chunks to your friends, and if you get enough of these chunks, you can recover your password. That resulted in a very fun user study, because what we had was we wanted to know, well, if someone called up your friends and tried to trick them into giving them the chunks, what would happen? So we brought people into the lab.
So if someone's having an affair, their spouse makes sure that their account gets closed, so they'll have to recover their password, and then they don't ask the spouse for help.
Well, no, it was more along the lines of, right, you're worried your spouse is having an affair, so you call up the person who's the friends of your spouse, and say, oh yeah, my spouse really needs her, she's lost her password, she's in the hospital, she really needs it, can you give me the codes? And so we brought people into the lab, and we could not run this study again, I think, without redoing the whole ethics for it, because we found out things about people we did not want to know. we brought in a pair of spouses, and it was each spouse's job to call the other. So we bring them into the lab. We asked them each to choose people who would be trustees for their accounts, who would be the people you would call in this situation. And then we told them, great, now take your spouse's list and see if you can get them to give up the code for the spouse, right? They'll log into the system, and the system's designed to, and the spouse had to consent, and they could watch each other and cut it off at any time. But it was basically the husband's job to call up the wife's friends and convince the friends to go to this system. The system would say, never give this to anyone but to that person, speaking to them on the phone or in person. And see whether the system was able to discourage them from giving it to the wrong people. And I remember one couple particularly well. Wife starts off, calls all the husband's friends. They trust her completely. So she gets all the codes in no time, because they know she's just a great person. And so who cares that the system says you should never give it to anyone but the person? They give her the wife all the codes. I do not know what had gone on in that relationship. And again, ethics rules would make it very hard for us to run the study again, given that we now know we learn certain things about couples when we run studies like this. Husband calls up the wife's friends, no dice. None of the codes. Right? We do not know what went on, why none of her friends trust him, but they do not. Right? And her account is secure from him ever. And so, really interesting study to run. And this is a system that Facebook now uses, a variant. I mean, they have, but yeah. So these systems are fun to build. They're even more fun to test.
Okay, I think this is a very good closing moment. So let's thank Stuart again for his talk and session. As always, you feel free to socialize and continue hanging out here. I think we have this room for until 12 o'clock. Yeah.
And any help with cleanup would be much appreciated.